what we have done in the earlier classes, we have started this analysis of strain after finishing the analysis of stress itself. You know, the state of strain at a point will be analyzed and will have to be analyzed here. In elementary strength of material, you know, two types of strains are introduced or discussed. One is longitudinal or extensional stress, means if a body is under tension, under tensile or compressive load, it will either extend or contract to its length, in x or in y direction. So, and secondly, the shear strain. If the body acts along on this particular surface, it will deform the concerned body to a certain degree, and this initial angle between the different faces will be disturbed to a certain extent. Now, above figure, what we have shown here, is the figure above illustrates to simple case of stresses itself. Now, in such a cases, the initial or undefined position of the element is indicated by full lines, and changed portion is by dotted lines. So here, this is the dotted lines, this is dotted lines, and this is dotted lines, and these are all formed lines because it is the initial undeformed position of our object itself. Now, with figure A, what happens? The element which was having original length delta x is deformed up to delta Vx, delta Ux, and the body B, the length which was along the y direction, it has length around delta y, which is deformed up to delta Uy. And at the point C, now what happens? The stress, we know by definition, strain is the rate of change of deformation per unit rate of deformation or deformation per unit divided by the original size or the original length of the body. So here, or f psi x denotes the linear strain or extensional strain, we defined as f psi x is equal to delta ux by delta x. In the same case, in delta y, in the y direction is given as f psi x is equal to delta ux divided by delta y itself. In figure C shows that shear strain tau or gamma xy in xy plane. What is the shear strain gamma xy? It is defined as the change in the original right angle between two line elements originally parallel to x-axis and y-axis. In this figure, the total change in the angle is theta 1 plus theta 2. What is given in the figure is here, you see, this is the original block which is given in formed line, and this is the position of the block after formation itself. Here you see this angle between this line and this line was 90 degree. It is defined. It is after deformation it is reduced, and this line which was originally parallel to x-axis is not deformed to take a new position at an angle theta 1 with x-axis itself, with the x direction itself. And this line which was originally parallel to y direction now deformed to a line by an angle theta 2 with the y direction itself. And this line after deformation, the position, this line itself from this point is moved to this point, which is given by delta Uy, and this point here is moved to this point, which is given by delta Ux. Now, reduction is initial right angle is considered to be positive shear strain. If we reduce what we have done, the initial right angle is reduced, then we think that is positive reaction, positive y-axis, and where in other corners, other diagonally opposite corners, it is also reduced. And what is the right and left diagonal corner? It is increased. Means shear stress there will be negative. But at this present formation, we'll consider only the positive shear strength. So what is going on here? Theta 1 and theta 2, which you have subtended, are extremely small. Then one can put theta 1 radians, means theta 1 in degree multiplied by pi by 180. Pi is 3.14 plus theta 2 in degree multiplied by pi by 180, where pi is in degree, which is equal to value of tan theta 1 and value of tan plus value of tan theta 2. So this two addition is equal, more or less equal to the two addition here, because both theta 1 theta 2 is very small in size. From figure, we know tan theta 1 is the deflection of the body along y-axis we have shown, that is delta uy by delta x, and tan theta 2 deflection of the body along x-axis by delta ux divided by delta y. Therefore, where delta ux here is the vertical and delta y is the base, here delta uy is the vertical, the delta x is the base itself. Therefore, the shear strain tau xy is tau xy theta 1 plus theta 2 is equal to tau uy, put the value of theta 1 and theta 2. So tau uy divided by tau x plus tau ux divided by tau y. This is the shear strain gamma, which is given by this equation here in equation number 4. Now, what happened? Reduction in initial right angle is considered to be a positive shear strain, since the positive shear stress compares are tau xy and tau yx, because cause a decrease in right angle. So initial right angle constitutes positive shear strain, since positive shear stress component tau x and tau yx, it causes a decrease in right angle itself. In addition to these two types of streams, a third type of strain is called the volumetric strain, which is also introduced here. Which is also induced here and given as the rate of change of volume per unit volume itself. We'll study all these strain in 3 dimensions, and we'll begin with the study of deformation like this. Now, what will be the deformation position itself? We have 3 rectangular standard of rectangular coordinate system here, that is OX, OY, and OZ, and we have a irregular shaped body here, which is shown at a firm line, and another irregular shaped body, which is shown as a dotted line, which will take this, because this shaped body, initial body, will take this final position after the deformation itself. Now, to study the deformation or change in the shape of the body, we compare a position of a material point. Compare the position of a material point before and after the deformation. First, we are thinking what is the position of a particular point exists over the particular body of itself, and what position it will take after the deformation itself. This is the line of discussion. It will be like this. Say we have a point P belongs to the body itself, and it has initial coordinates x, y, z, means OX, OY, and OZ is given as x and y and z. Now it is displaced after deformation to P dash, and with this coordinates then is given as x dash, P dash is equal to x dash, y dash, z dash. So P dash along OX is equal to x dash at the point P along y is equal to, along the coordinates y is given as y dash, and at the point P the coordinates along z is given as z dash itself. Now, since P is displaced or moved to the position P dash itself, then you see the gradients, that the segment P and P dash is a vector segment. This displacement of P to P dash is a vector. You know, as for our definition of vector analysis, the force, displacement, velocity and acceleration are vectors, means it has the magnitude as well as direction. It can have the same vectors of same magnitude in different direction. They are not same, they are different. And other items which have only value and they have no have a particular direction. In any direction they are same. But vectors, they are not same in all direction. They may have the same length, but as per their direction they are different. So here we are saying that displacement here p to p dash is displaced from p to p dash is a definite direction. It is a vector and defined as displacement vector and denoted by u. So p dash displacement defined as displacement vector and it is defined by p u itself. Now this displacement vector u, which is a straight line originally or with a certain distance, it must have certain coefficient along x-axis, y-axis, and z-axis. These coefficients are given as ux along x-axis, uy on y-axis, and uz along z-axis itself. The displacement vector u has components like this. So we can write the displacement vectors as per definition of vector analysis. U is equal to I ux j plus j uy plus j, u zx. भूल बोला k u z I z k. That this displacement undergone by any point is a function of its initial coordinate itself. What is this given here? It is depending on the function of its initial coordinates. So displacement is starting from the point P. He has a specific coordinate. So it is displacement definitely on the position of the P, means definitely on the position initial coordinates of P itself. Now, if we assume that this displacement is defined throughout this volume, then the displacement vector, that is displacement vector for a particular body throughout this volume, is known or given to us. Then the coordinates if the coordinates are known and its coordinates are supposed to be known, because unless you know the coordinates, you cannot place a distance from a particular point to another point. So here you are supposed to draw this displacement line. We are supposed to know the coordinates of its ends, otherwise you cannot draw the displacement vector. So then we can say that a displacement vector field has been defined throughout the body of this body. If it's been defined, then we can say if the coordinates are known, the displacement vector is defined throughout the length of the body. So we should have both. We should know the displacement vector and we should know the coordinates of its ends. Well, then you can use this for any point throughout the length of the body itself. If r is the position vector of the point P, means if we know what is the position of the r of the point P, means what is the coordinates of P, then if we know the position vector of the point P or what is the coordinate of the point P dash is given that in terms of r, then r dash will be given by u r, the position vector at point P, plus the distance vector u. Then distance vector is the difference between the position vector at r dash minus the position vector at r. For example, the displacement field for a body is given by u x square plus y into I plus 3 plus z into j. There's a problem is given. What in the problem, what is given? That displacement vector u is given, which is given as x square y into I plus 3 plus z into j plus x square plus 2y into k. So the vectors at vectors x, y, and z direction, that ux, uy, and uz of this displacement field is given here in terms of x, y, and z itself. The default position of the point originally was 3, 2, and 1. What will be our question is, what is the deformed position of the body when it was originally 3, 1, and minus 2? So we have original position vectors at u, the and displacement vector is also given to do it. So what will be the displacement vector at 3, 2, 1, minus 2 when x, y, and minus z is given. So the displacement vector at the point P will be given as, by putting this value of x, y, and z here, 3 square plus 1 into I, 3 minus 2 is because z is plus z is equal to minus 2, and 3 square plus 2 into k. So 10I plus j plus 11k. The initial position vector of the point P is given as, so u is given as displacement vector is given 10 plus j plus 11 plus k. The initial position vector is given of the point P is also given as, this is x, y, and minus z. As x is put here, the position vector 3I plus z minus 2. So we have calculated both the displacement vector and we have calculated the position vector of the point P. Now we are supposed to go the displacement position vector uh, after the deformation. What is the deformation of the position vector itself? Now, the final position of vector at the point P dash is given as r dash is equal to r plus u. So we have to add these two vectors. This is vector and position vector here to know the position vector at r dash is given as, if we add them together, you get 13I plus 2j plus 9k. Let us go to another problem itself. The two points P and Q in the order-formed body have coordinates 0, 0, 1, and 2, 0, minus 1. So 2 points are given here, those coordinates also given here. And assuming that the displacement field given in the earlier example, so we can use here the displacement field itself has become, due to the imposed by to the body, a force has been imposed to the body, that what is the distance between the point P dash and P and Q dash after the deformation itself. So here we are assuming we know the coordinates of the original points P and Q. We know the displacement field, and we are supposed to know the different distance, or what you said, the displacement vector of the point of displacement vector of P between P dash and Q dash, where P dash and Q dash is the point acquired by P and Q after the deformation itself. So at point P, we can find out the displacement vector first. That is, if we put the value of x and y and z in our displacement field, we'll get 0 plus 0, 0 plus I, 0 plus 0 into k into 4j. So here we got the at the position vector at the point P itself. That is equal to 4j. Their displacement components are ux, where the displacement components, the displacement vector at point P here is given by this thing, where the displacement points are ux equal to 0, uy equal to 0, as equals uz is equal to 0, uy is equal to 4. The final coordinates of P after the deformation will be P x plus ux, 0 plus 0 to 1, P dash is equal to x plus ux, 0 plus u equal to 1, x, y plus uy, 0 plus 4 is equal to 4, and z plus uz, 1 plus 0 is equal to 1. So P dash becomes 0, 1, or coordinates of P dash become 0, 1, and 4, 0, 4, and 1. Now let us go for the displacement component at point Q, which is uh, given as ux is equal to 4, uz is equal to 2, and uz is equal to 4 by putting the coordinates q in our displacement field. There ux, uy, and gz becomes 4, 2, and ux 4, 2, and z is equal to 4. The coordinates are already given. The coordinates are q. Coordinates q is given. So q dash, coordinates of q dash, will have to add ux with x, uy with y, and uz with z of point P dash. So this, after adding to it, will be 6, 2, and 3. The distance p dash q will not now will be equal to the difference between between the two coordinates p dash and q dash is square and whole square root of it in plus difference between the coordinate of x coordinates of p dash and q dash and its square plus difference between the y coordinates of q dash and p dash, that is its square plus and the difference between the z coordinates of u and s and its square and whole under is square root, which is given as 2 into square root of 11 itself. Thus we got the distance p dash and q dash. Now let us find out the deformation in the neighborhood of a point P. At the point P, let P be a point in the body with coordinates x, y, and z. What we have here, we are ox, oy, oz. What we have here, P dash, P and Q. What is have here, P and Q, whose coordinates are given. These coordinates given as P x, y, z, and first of all, this is our the body with it, which is in the conform line, and this is the coordinate of the position of the body after deformation itself. Now we have the point P here, whose coordinates are given to us, and we have the points Q here, whose coordinates are given like this way: x plus delta x, y plus delta y, z plus delta y, delta y. Because we are considering a very small region surrounding y, and q is one of the point within this region. As region is very small, the difference between the coordinates will be infinitesimally small, but they are not same of course. So this small increment delta x, small delta y, and delta z is added to x, y, and z respectively to know the coordinates of the point q. Now when the body undergoes deformation at the point P and Q, move towards P dash and Q dash. when we know what is the points P dash and what is the point Q dash. So because we are supposed to know that this coordinates at P and coordinates at Q dash. Let the displacement vector u at position have the components ux, uy, and uz. So we have a displacement vector here, and at the point P, and in any direction we can use the value of ux, value of uz, and value of uy at point P itself. So we have added P dash, that becomes P plus displacement vector ux, which is actually in terms the portion of what is this, the pp p to p there, what is the components of the length pp along x direction, y direction, and z direction. So ux, we have the components ux, y, z. So at p dash will become x plus delta x, p dash is become x plus ux plus equal to y plus uz plus z plus uz, and qx is given already x plus delta x, y plus delta y, and z plus delta z. Now when the body undergoes deformation, the point P and Q moves to point P dash and Q dash. So the displacement vector u at P, just I'm expressing it. Stop share and go for just I'm telling you a few points about the vector analysis, which is already known to you. Now, any vector in 3 dimensions can be represented with an initial point O 0, 0, 0 and endpoint A1, A2, A3. So vector has the initial point 0 and final point a1, a2. Then vector ai, a1, I, a2, j, a3, k is called the component vectors of A. The x, y, z direction and the state scalars a1, a2, a3 is called the component of A in x, y, z direction. Just have to know what is ux and uy and uj. So the sum of this a1j, a2j, and a3j is the vectors of A. So we may write a is equal to a1i plus a2j plus a3k, a3k, a1i plus a2j plus a3k is the vector A. And the magnitude of the vector is given as both the parallel lines between A, square root of a1 square plus a2 square plus a3 square. The consider a point P, the x, the vector from the origin to the point P is called the position vector. These vectors are given as x, y, and z itself. And this magnitude is square root of r square, x square, and z square. Now, we have the components ux, uy, and uz from the scalar itself. So the coordinates of P and P dash and Q is given as P, X, Y, Z, X, comma, Y, comma, Z, comma, P dash X plus dux, Y plus ux, Y plus X, Z plus uz, and Q is given as X plus ux, Y plus uy, and Z plus uz, Z plus delta Z, X plus delta X, Y plus delta Y, delta Z plus delta Z. Now we know due to deformation, Q, when the original point Q is also displaced, displaced, uh, displaced, and the displacement components of Q is differ very complex from those from P, since Q is away from P by delta X, delta Y, and delta Z. So consequently, we the displacement of Q, we are assumed that ux plus delta ux and uy plus delta y, uy, and uz plus delta uz. The displacement at q, we are using the same value and same change of value of delta ux and uy and uz. Originally it was ux here, and it is becomes delta ux plus delta uy, delta uz. So if q is so if cq is very close to p, then do first after approximation delta ux. What will be the delta ux itself? The rate of change of ux in terms of along x direction multiplied by delta x itself. Originally, this change was the difference was here. What you have said ux plus delta ux. So what will be the delta ux here? We are differentiating delta ux by in terms of x, or rate of change of delta x in terms of from x multiplied the actual change, actual difference delta x. So initially from x it was changed to ux, and initially from delta ux you have to change this. It, initially from x we are changing to delta x, and initially from ux we are changing to delta ux, and this value is given by this formula. Delta ux change of delta ux in terms of y into delta y, delta u in terms of z into delta z. The first term on the right hand side, the rate of change of ux, okay, multiplied the distance traversed, and the second time is the rate of increase of ux in y direction multiplied by the distance traversed in z direction. That is delta y. Similarly, we can also repeat the third term for delta ux and delta uy and delta ux. So both delta uy and delta uz is given over this equation. So let us explain it again like this. Initially the components, initially the position vector, displacement vector have the components ux, uy, and uz at p. P has the coordinates x, y, and z, and P dash has the coordinate x plus ux, y plus uz, z plus uz. As Q is very close to P, we think that their coordinates is just increase a very small amount, x plus delta x, y plus delta y, and z plus delta z. Next, after deformation, the displacement of Q from this position, from these coordinates will have ux plus delta ux, and delta u, here we have added the displacement with p, but here for ux we have, as it is not exactly equal to x plus but it is equal to delta x, if there is a change in ux in the q direction, that is delta ux, the delta uy and delta uj. How will you get delta value of q? The first order approximation delta Vx will be rate of change of Vx along x direction multiplied by the original change delta x plus rate of change of Vx in y direction multiplied by the original y, and rate of change of Uz by delta Uz multiplied by the original position delta j. The first term on the right hand side is the rate of increase of ux in x direction multiplied by the distance traversed delta x. Second term, the rate of increase of ux in y direction. Third term, rate of increase in z direction and added by and multiplied by the actual increase in the x, y, and z direction respectively. So ux, uy, and uz we have created and plotted accordingly. So what we are doing now, the coordinates of q, are q dash delta delta x ux plus delta x, y delta y, uy plus delta uy, and z delta z plus uz plus delta z. Before the deformation, the segment PQ has component delta x and delta y and delta z along three axes. After deformation, the Z has component delta x plus delta ux, delta y plus delta uz, delta y z along the three axes itself. The terms like delta ux and delta x, delta ux by delta y are important for the analysis of the strain itself. These are the gradients of the displacement component at P in xy direction. One can represent the form of a matrix called the displacement gradient matrix as delta uy by xj, delta ux like this, delta uy, delta uy by ux, uz uy, delta y delta x, delta y ux delta x like this, and delta ux delta y, this is around delta y delta z itself. Let us have an example. The following displacement field is imposed on a body. What is given as x, y, z, I, 3 into x square z into I plus 4k whole multiplied by 10 to the power minus 2 or multiplied by 100. Consider a point P and a neighboring point Q where PQ has the coordinate cosine. So ux 0 plus 200 ny is like this. Are the following direction cosine? Well, PQ has the following direction cosine, or the component of x, component of this displacement vector along x and y on direction, which can be achieved only by having the cosine of the angle in between angle, and this is the direction cosine which is given here, nx, ny, and nz. Now point P has the coordinates 2, 3, point P. If point PQ delta is found from the coordinates of P dash Q, to find the components of P dash Q dash after the deformation. Now we have the displacement field on the body P, and we know the coordinates of the point P, and we know the coordinates of the displacement vector P to P dash, ux, uy, and uz3, and we are supposed to know all these things, components of PQ after the deformation. Before the deformation, PQ were nx, components of PQ, nx are delta x, delta s, delta x is nx1 delta x, nx multiplied by delta x, 0.2 is given, multiplied by delta x, ny 0.28 is given, multiplied by delta x, point z is given, multiplied by delta x itself. From 1 to 3, the values of delta ux, delta uy, and delta z can be calculated. We are using p to the power minus 2. So delta ux by delta x into py, delta uy by delta x into py, and delta p is equal to 0 itself. Px 6 py, px, and py itself. So thus delta ux and uy, px, delta uy, pz, and px square, delta uz by delta y is equal to 0. Let us stop the share here.